Thanks for the organizer for the invitation, and thanks for everyone for coming. The topic actually has been addressed by several previous speakers. We want a model to be able to reason, but that's clearly not the only thing we want. We want the model to reason correctly in a certain sense, and also we want it to work in a realistic environment. Okay. So these two requirements or expectations seems to be conflict with each other. If we just want a normative model of reasoning, there are already a whole bunch of them. Okay, that's studied by mathematicians, logicians, and computer scientists. But the common issue about all of them is they tend to be highly idealized. Okay. So it's not really working in a realistic environment. But what realistic environment actually means, this is not a well-defined concept. At least in my model, I mean the following three keywords. The first one is finite. The system must only use finite information processing power in terms of CPU, memory space, and so on. Second one, it needs to work in real time, make real-time response, meaning that actually every task or problem have some time pressure associated with it. You cannot just work on it as long as you want. The third one is it needs to be open, meaning especially open to unanticipated tasks. Okay? It's in this sense, the work is referred to be general purpose, which does not mean it can solve all problems. There is no such a thing. Instead, it can solve problems not anticipated by neither the designer nor the system itself. Okay. But of course, there is no guarantee that it will work properly because it's a surprise, it's something new. So altogether, this is what I call the assumption of insufficient knowledge and resource, which is the foundation of all of my previous works. Okay. One consequence is very clear, obvious. That is, there is no absolute truth can be guaranteed anymore because there are a lot of things you don't know, and also you cannot promise absolute optimum solution because you don't have the time to think about all possibilities. Okay? So if that's the case, what is the norm of reasoning? So what is the right or valid or correct reasoning if you cannot even guarantee the correctness of the conclusion? To me, it's adaptation or adaptability. Actually, this is also something suggested also by some previous researcher. I'm not the only one, of course, to think in this way. Adaptation in this context means, first, you don't know the future. You have to depend on your past experience to make prediction, which can be wrong because the future is different. But that's the only thing you can do. Second, you don't really have the time, especially time, also memory space, to satisfy all the requirements. But it doesn't mean anything works equally well. Okay? You need to do your best, according to your experience. Okay? Try to allocate your memory as reasonable, as efficient as possible, again, according to your judgment. Okay? So, in this environment, valid reasoning does not guarantee always correct anymore, like in traditional logic models, which is good. I'm not saying that's bad. It's just not realistic in real situations. So instead, what I'm after is try to be adaptive and try to be as efficient as possible. Okay. So today I'm going to very briefly introduce a concrete model which has been formalized to a large extent and also computerized, implemented in several prototypes, okay, which is called NARS for non-axiomatic reasoning system. I'll start with semantics, which basically, according to what I have said, this is guaranteed that semantics, you see, the central concept in semantics, one is meaning, one is truth, right? So in this context, we don't have truth in the traditional sense anymore, but we still have the concept of true or false. In this sense, is judged according to the system's experience. That is, as true as I know. Here, I means the system itself. Okay? So here, the system's beliefs are not description about the world. Instead, is summarized experience of the system. So there is one basic conceptual relation, which is what I call inheritance, which roughly speaking is a generalization relationship. For example, the simplest sentence or statement in my system is a subject term. Inheritance, that's what the arrowhead means, a predicate term. Okay. So it's kind of like, intuitively speaking, is saying that S is a type of P. That's technically is also something very different from the traditional logic. Especially now, logic have been dominated by mathematical logic for decades. But this one is closer actually to an even older version of logic. That's Aristotle's syllogistic, later we'll see. Then this F and the C is the truth value. By truth value, actually in NARS, it means a pair of real numbers between 0 and 1, not one single number. So again, this truth does not compare this statement with the reality or fact or state of affair, whatever you call it, as in traditional logic. Instead, it measures available evidential support, which has been taken into consideration. Okay. This pair of numbers, the first one is called frequency, which is the proportion of positive evidence among all evidence taken into consideration. Here, I don't have the time to define what is evidence in this context, which is explained in my papers and books. But intuitively speaking, this one is easy to get. It's kind of like subjective probability, okay? But you see, it does not take a limit. The limit is in the future, which the system have no idea. Okay, just among what you know, what's the percent of evidence that support this conclusion? And the second one is unique in my model, which is called confidence. But it's not the confidence used in many other models, even though they have the same intuition behind. Okay. This is how sure you are about your opinion. Here, you'll see this confidence is also a ratio. This W is the amount of evidence you have already collected so far, divided by W plus K. Here, K is a positive constant, which is a system parameter. By default, you can think it as 1, which actually indicate a certain amount of future evidence, which is taken to be compared with what you already know. Okay? So it's kind of like how much you already know compared to the next piece of information or evidence that to be collected. So actually, this formula, even though it's very simple, it shows the very basic spirit of what I call non-axiomatic logic. There is no absolute truth. The system is never completely confident about its judgment, okay? Because W is always smaller than W plus 1. But you see that as the system is collecting more and more evidence, it will become more and more confident about its conclusion, okay? Even though it doesn't guarantee that it's going to be closer to the reality, especially when we are assuming the reality is changing over time. So based on this representation, the inference rules are also closer to Aristotle's syllogistic reasoning rule, compared to, say, mathematical logic or first-order predicate calculus, which is now dominating the research. So These are the basic rules. There is actually a large number of rules, but today we can only talk about the very basic. The first one, this triangle is the deduction rule. Okay, one form or the simplest form of deduction rule, which basically, intuitively speaking, is say from two premises, if S is a type of M, M is a type of P, then of course you can derive S is a type of P, which is just transitivity, right? This inheritance relation in its idealized form clearly is transitive. So I don't think anyone have a problem here. The only issue in NARS is, of course, now everything is true to a degree. So there is a truth value function associated with this rule, which calculates the truth value of the conclusion according to the truth value of the premises. Again, we skip that. Okay? But you can think, if the premise close to absolutely true because like very high confidence, the conclusion will also have a very, very high confidence value. So this is trivial. The interesting one are the following two: abduction and induction, okay? Which looks very similar to deduction, but if you pay close attention, you will see the direction is the difference is in the direction of the arrowhead. Okay. Actually, this definition also is not invented by me, but it's by C.S. Peirce. Okay. He introduced abduction and induction in the context of term logic by switching the conclusion of deduction with one of the premises, because there are two premises. Okay. If you switch with one, you get induction. You switch with the other, you get abduction. That's from C.S. Peirce's work. Okay. But this is very clearly the case. Well known in the history of logic and philosophy, that is, abduction and induction does not guarantee truth in the traditional sense. Okay. You can get true false conclusion from two premises if you use this pattern. Peirce himself realized this, and he just said, this tool just gave us useful hypothesis. Okay. So spatially abduction gave us explanation, and induction gave us generalization. But in NARS, we can make it justifiable because now truth become a matter of degree. Furthermore, this matter of degree is not about the reality, instead is about amount of evidence. So in this case, both abduction and induction have a truth value function in NARS, which will get a truth value, except even if both premises are absolutely confident or close to high confident, okay, the conclusion is only true to a very low confidence because there is at most only one piece of evidence. Using the previous truth value function, you can calculate the result. Okay, the confidence of the abduction and induction will always be lower than 0.5. Okay? And finally, we have a revision. So how can you get a high confidence conclusion from induction and abduction? Well, if you have a lot of evidence. So revision is basically evidence accumulation, which is just add the amount of positive and total evidence together. Okay. So if you have more and more and more, you get accumulation or high confidence conclusion. Which also handle conflicts. Another property of NARS is it does not require consistent information. Okay? You can give it conflict information, which can be conflict in the traditional logical sense or probabilistic sense. Okay? You can tell it, the frequency is 0.5, then you tell it, no, it's 0.3. It will not make the system crash. Okay? But of course, simply because the system doesn't truly believe any of them, okay, but they will take them into consideration. as evidence of different amount of support. So in this way, you see a nice thing about term logic, or this form of term logic, is you can see everything now become a graph operation. Okay? So the system, at this level, the system's knowledge become a concept graph. Every node corresponds to a term, every link corresponds to a sentence or a statement, which is directed and weighted. Here, the weight value is it's a pair of numbers. That's the truth value I just mentioned. Okay? And actually, there's different types of links. Now you see some of them red, some of them are black. Okay, the black one and the one I just mentioned before, that's the system's belief. That's the kind of like background knowledge. The red one, on the other hand, are the tasks the system wants to process or need to process. As a reasoning system, at this level, the system has two types of tasks. One is what I call judgment, which is basically new information. Another type is question, to be answered according to the current knowledge. Okay? For example, here, this red one is kind of like, I tell the system that swan is a type of bird with an initial given truth value. Okay? And this one, you see, is an arrowhead from robin to swimmer with a question mark, which is kind of like a question saying, you tell me what is the truth value according to your knowledge. And finally, also, you can have a question mark for a term which is unknown. It's kind of like, now tell me a special type of robin, like yes, no question and WH type of question, okay, separately. So then what we call a concept in NARS is a node with all the directly associated belief and the task. Okay? So it's a data structure. Like bird is, what the system know about a bird and what the system is thinking about a bird. Okay? And you see, this one is also going to turn black after it's been processed for a little. But at the very beginning, every new piece of information will be used for forward reasoning. It's kind of like not just remember it. The system will think about what that means, try to figure out its implication using the available inference rule. Okay? So every inference step in this highly simplified model is, you see, it can be very simple. It just each time you pick a node, you pick a red link, you pick a black link. Okay? Their combination will decide which rule can be applied to it. And then you're going to derive new red links, and also the red links will gradually become black. You can just visualize it in that way. So another interesting thing is, you see, I said the system can handle unanticipated tasks, which means what? Which means it does not have a fixed procedure for any given question or given input. Okay? For example, since if we think, there are already 1,000 of properties known for bird, then now I ask it a question or give it a piece of new information about the bird and which one you should take into consideration. Again, according to my insufficient knowledge resource assumption, exhaustive search is not allowed. Okay, each time you can only think about one thing, and which one? You see, the system uses a priority-based resource allocation, meaning that everyone have a chance, but the chance are different. It depends on its priority, which is also a measurement, is a real number between 0 and 1, which is a summary of a whole bunch of relevant properties, like, for example, urgency, like some type new task, you can say this is urgent, you can say this is not urgent, you can think about it when you have the time, and so on, and to a different degree. And usefulness is based on usage history in the past. Some of things will be more useful than some other things according to systems experience. And simplicity, this is more, at the current stage, they're all very simple. Later we'll see some of them will become complicated with an internal structure. And the relevance, which is kind of like activation spreading, like in neural network. So currently, for example, everything directly related to the given question will have a higher relevance and also higher priority, everything else being the same. Okay. So in this sense, you can see that with limited resource, especially processing time, the system only use part of, actually a very small part of its knowledge or its belief. Okay. Also, the processing for different tasks also prioritized. Conceptually speaking, they're all processed in parallel, but at different speed to different depths. Okay. This is more, I will say, more similar to what attention means in psychology compared to the use of attention in the current large language model. Okay? So this is also what we call a concept-centered representation. Like you see, everything is a concept. Here we are using concept in a very broad sense. Okay? It's a data structure. It's based, it comes from the system's experience. It's used highly selectively. Okay? Even within one concept, the task and the beliefs under active processing is only a small part in general, but that distribution will change over time according to history and context. And also another thing I didn't explain, but you can guess, what a concept means to the system is not determined by its reference to objects in the world. Instead, it's by what the system knows about it. That's why it's called experience-grounded semantics. So yeah, terms are just the names or identifiers of concepts. And also, we have a whole bunch of rules, which I don't have the time to explain, to build compound terms from existing terms to capture structures or patterns that actually appear in a system's experience instead of try all possible combinations. So in this way, the system can have new concepts from several different sources. One is novel experience. You can mention a term you never heard before. Okay? And also there is attention shifting. As you can see that all the factors I mentioned change from time to time. And also there is this compounding process. The system is using the existing terms to build a more complicated one to more efficiently summarize its experience. Now, symbolic reasoning, well, some people may think, oh, everything you just said is nothing but symbolic reasoning. In a very broad sense, yes. Okay. In that sense, actually, I can even argue everything happening in a computer are symbolic because eventually it's just binary strings. Okay. But symbolic reasoning in cognitive science and in AI actually has very special usage. That is, when we say something is a symbol, we mean it can be interpreted in multiple ways. That is where the symbol grounding problem or Chinese room argument come from. Okay? If you don't know its interpretation, you don't know its meaning. That is already, as I explained, is no longer the case in a model like NARS. Okay? The terms are grounded in its own experience. You don't need any separate interpretation to tell the system what bird means. Okay? Of course, it doesn't mean the same thing as to us. But to system, it just means whatever it has seen before about that term. But in this situation, we still have something called symbolic reasoning in NARS, which, as I already said, in a very general sense, symbols means that something represents something else. Okay? So a term representing a concept in that sense is already a symbol. But the symbolic terms represent not other concepts. It represents other terms, which is more like a variable in mathematics or a pronoun in natural language. So, and this kind of terms indeed can have multiple interpretation within NARS. Okay? And also we have linguistic terms in communication language which represent other terms within the system. And also, even though I have claimed there is no absolute truth, and some of you, especially the mathematicians, will say, oh, how about 1 + 1 = 2? Of course, that's absolutely true. Okay, it's not have a confidence, to a certain level. But that's a local truth. That's a truth within a subsystem. So we can have a subsystem defined kind of like separate from the empirical beliefs, okay? And also for those subsystems and the terms within those subsystems, that's like this part. We do have the mechanism of interpretation which temporally related to some concrete term as an interpretation of it. And you can have different one in different time. Okay? So yeah, we do have a symbol grounding issue, but that's not for every term, but only for kind of like the mathematical term or abstract term in the system, okay? Which can be applied to different contexts to mean different things. And also within that subsystem, we do not use the inference rule I just mentioned. We use binary inference rules, just like in traditional mathematics and logic. So you don't have a degree of truth there. True is true. Okay? And another extension, or a bunch of extensions, I don't have the time for detail, is how about the sensory motor? Okay. We have definition of events, which are nothing but a statement whose truth value change over time or depend on time. We have operations, which are the things that the system can execute, can turn it into true, can make it true, or can realize. And we have goals, and the system try to realize. Okay, so this part is, you can think, is very similar. The basic idea comes from logic programming, okay, like in Prolog and that kind of system. It just, we also extended that from binary logic into a multi-valued situation. So it can be true to a degree, or you can make it true as much as you can, that kind of stuff. Okay? But the basic idea is already there. And we also have the system in this way can have sensory motor experience, okay, which is based on spatial temporal relations and coming into the system. Actually, we already have several implementations which control simple agents in a game environment or physical robots running around, okay, using this logic. And the learning of the system's behavior is based on a schema theory, and sensory motor contingency is kind of like, yeah, whenever you do A, you always see B, or you usually see B, and the system will believe A will cause B to happen, and that kind of thing, even though the belief can be wrong, and will later change it and try to learn more efficient one. And the current working is also include internal experience. That is, to a certain degree, the system will have internal sensor and actuator. It will know what is happening within itself. Here itself, meaning the reasoning model itself, and try to control it to a certain degree. Okay? It cannot control everything or know everything about itself, but it will know some. and try to learn about how to use that. So this is a graph. You can see, again, this is also the concept graph I mentioned before. It's just now much more complicated. Now, some of the terms will directly correspond to the executable code, and some of them correspond to some mental image or some sensory patterns. But one thing we decided at the very beginning, which is also controversial, I guess, is the system itself does not have any built-in sensor and actuator. Instead, it has an interface, again, a general purpose interface, which allow different sensors and actuators to be plugged in. As far as if follow the same interface protocol, that is, I can send you operation and you can execute that, you send me back the result according to your sensation. Okay. So in this way, for example, we don't assume the system must have vision, but we do assume the system must interact with the physical world and take something back, for example, using a radar or sonar or something like that. Okay. And also, when it move around, for example, when we put it into a robot, we don't assume anything about the robot have 4 wheels or have 2 legs or have anything else. We just say there's some actuator, you can call it, and then it will run, you will see some difference, okay, using your sensor. So you form a closed loop using your sensor and actuator, and the system itself is just a logic which will handle that interaction with the physical world and try to learn how to interact with the world according to its goals and the tasks, which also involve overtime. So you'll see this is clearly a very complicated system. Here I can only talk about the very basic. We have applications, we have implementations, we have, actually the implementations are open source. You can take a look at our source code and demos online. And also a lot of publications, including several books. Okay. Another thing you have seen that clearly, at least you can see that is very different from large language model. Okay, even though both claim to be moving toward AGI. Okay, one thing. But on the other hand, they're actually, I don't think we are competitors of each other because we are actually after very different understanding of what intelligence means. Okay. NARS never tried to duplicate the human brain or human mind at the neural level or even psychological level. Okay. Instead, we try to be much more abstract than that. We are not saying that this is the right thing to do. We just say we get different result. Okay? It will serve different purpose. Okay? So the first, you see, since we do not assume we have, the model will necessarily have human-like sensor and actuator, its experience clearly will be different. Since its belief and concepts, abstractions or generalizations from its experience, is mind, and the content of the mind will be very different. We never try to posit a Turing test. Okay? It's just simply because, to me, that's a too limited vision about what intelligence means. Okay? But on the other hand, we believe the mechanism, for example, the type of reasoning, okay, should be designed or can be designed independent of the concrete sensors and actuators and the concrete experience, especially it doesn't have to be human experience, but it needs to have its own experience and try to generalize from that and try to adapt to its environment, which does not necessarily to be the same to our environment. Even though clearly there will be a lot of similarity, there will be a lot of overlap. Okay, that's for sure. So if we talk about the similarity, you see that actually NARS provide a comprehensive interpretation of many psychological phenomena. I myself, even though I was trained initially in computer science, my doctorate degree is a joint degree with cognitive science, so from Indiana University. So I learned a lot of psychology and some neuroscience and linguistics and a whole bunch of other stuff. Okay. And we have publication about interpretation of some psychological experiment result, say Wilson's selection task, so-called confirmation fallacy, and so on. Okay, we can explain why humans do it that way using NARS. Actually, NARS will do the same because when you work with insufficient knowledge resource, what is taken to be right and wrong actually is different compared to traditional models, especially mathematical logic and the probability theory. Okay, and they're good, but they works in idealized environment. In realistic situation, their applicable assumption or condition does not really apply. Okay, it's not satisfying. Okay. For example, just one thing, consistency, which of course is good, but why we are not really consistent? I haven't really met any single person who is completely consistent, simply because our environment does not allow that. Okay? We can take that as our goal, and also NARS, you see, always try to be consistent and by resolving its internal conflicts, but it cannot always guarantee to be successful. But it will try its best. Okay? To me, that's what intelligence is really about. Instead of guarantee to be always correct. Okay? That's to me, that's beyond intelligence. Okay? That's not possible. So what I can say about large language model, well, clearly, to me, reasoning and reasoning in large language model are very different thing. Okay? Even though now I tend to agree that large language model can do reasoning, but it's not the type of reasoning I'm after. It's more like a descriptive model, okay, of human reasoning. It summarizes human reasoning results and also repeat human reasoning mistakes and bias. Okay? So there are a lot of issues. Actually, several speakers have already mentioned the issues in reasoning in large language models, so I don't have to repeat any of them. Okay, I assume they already know them. Okay. What I want to add is I don't think those issues can be resolved by adding more data or more computational power, simply because that's in their DNA. Okay? That's in the basic assumption of all those models, and in their goal is to duplicate human behavior and predict what the humans say in that environment. To me, it's a good goal, but it does not really cover everything under the consideration of artificial intelligence and cognitive science in the general sense. So I know my talk may actually raise more questions than answers. So here I have some reference so that you're interested, you can take a look, and we still have time to discuss some of the details. So I will be very glad to provide additional explanation to anyone interested. Okay, that's all.
Any quick question? You said your work spans two domains, cognitive science and psychology and AI. What, in your view, are the key kind of outstanding questions around psychology and how animal works that could also inform how we can trust the
To me, there are still a lot of lessons that AI need to learn from psychology. Even though large language model claim to be learned from human brain, we know that actually a lot of work is actually from mathematical consideration. Say whether a certain function can converge and how fast they can converge and that kind of thing. For human psychology, I think one thing I learned is this, what I mentioned in the title, that is realistic situation. Actually, several psychologists already mentioned very clearly human intelligence developed in an environment where too much information, too little resource, and not enough information processing power. For example, the concept of attention directly comes from the selective processing, the necessity of that. Okay. I think all those things we need to actually learn from psychology rather than just on the superficial level try to pretend to be a human. To me, that's interesting, but it's not deep enough. We need to learn to go deeper.
Yeah, you said something earlier as well, that you find belief.
Mm-hmm. Yeah. For example, how the human beliefs are influenced by its own experience, and whether you can really completely conform or disconform a certain belief, which, we already there are a lot of things in psychology which shows that how someone's experience influence their judgment. Okay, all those kind of things. I think we should. And also that raises an interesting question. If the computer system does not have that experience at all, how can you expect it to have the same belief as we do?
Slightly left field question. In humans who may not have developed language, what is known about the mechanisms of reason?
Good question. Actually, you'll see that there is my belief, okay, which is come from my experience, is that I'm using logic in a different sense, like mathematical logic, probabilistic logic. I'm not really talking about, in our mind, we have a set of formal rules we follow. That's clearly not the case. But we do have some regularity. So I'm trying to capture that regularity and in computer and in mathematical language, even though it doesn't mean I'm not claiming that's exactly what we have. So in that spirit, we believe that even with our thinking, a lot of part of our thinking is outside language. But my claim is following the same logic. For example, generalization, okay, which happens even in low-level perception. But we do have this transitivity. For example, if A can be generalized into B, B can be generalized into C, then A will be seen as a type of C. Okay, that does not really depend on any language, unless you say, you have an internal representation and we use that as a language. And also, say, induction. You see A followed by B. That repeated many times, you're going to form that pattern. That's classical conditioning. Again, that's psychology, okay, which can be wrong, of course, but that will be formed without language in the narrow sense.
Thank you.
Happy to use yours. Thanks.
Telling you will be your chair.
Oh, great. Okay.